Hi, my name is Peter Barendse. I work in the Wolfram Alpha Math Content Group, and I'm talking about generating step-by-step explanations and proofs for education. So first, a little context and motivation. Is this good font, or should I turn it up? Maybe a little bit. Okay. Got some white space on the bottom. So off the bat, I want to say a main purpose of this talk is to reach out to educators and students for ideas and feedback about how we can improve our step-by-step coverage and how we can use these programs in some different ways. So feel free to raise questions in my talk. So if you haven't seen step-by-step, I'm going to show you some examples in Wolfram Alpha. But it's a multidisciplinary effort, and it's a blending of two very different worlds, right? The highly abstract world of math logic and programming, and the more practical world of education. So I've been a part of both worlds. When I got my PhD in mathematical logic, there's not a lot of research funding for set theorists, so I taught pretty much every semester. And before that and after that, I've taught some college classes in high school. So I've seen how these worlds actually don't interact that much, and actually they're interacting, I think, less and less as mathematical theory proceeds farther away from the basic educational things that we teach students. So a little personal bit, so maybe I should flip my little thing around for a second. A little personal view of Wolfram Alpha's step-by-step and homework and computer-based math, because I think it deserves a little to be addressed a little bit. So since we've had calculators in the classroom, students have been asking, why do I have to learn this if my calculator can do it? Right? And we've heard this from the start at Wolfram Alpha. Why do I have to do this if Wolfram Alpha can do it? And so now students with the step-by-step can ask an even harder question, right? Why do I have to learn this if not only can my computer do it, but can also understand and present an explanation that even I can understand, right? So the answer, I think the computer-based math answer is you shouldn't, right? You shouldn't be teaching you algorithms. We should teach you how to manage computational processes and think about big questions and how to address them using algorithms that you just know exist. So I'm very pro computer-based math. But you might be asking, so why are we writing these algorithms? Why are we generating these step-by-step programs to teach these classical algorithms that we could argue maybe students shouldn't be learning? Well, I see it as not contrary to computer-based math, not exactly complementary either, but sort of maybe orthogonal. So one comparison I'd like to make is the story of John von Neumann, who you might have know this story. He's famous for going to the backs of math, science, and physics books and reading all the formulas and memorizing as many formulas as he could. And in that way, he could, pick out, apply different formulas and algorithms to different research areas and make some amazing contributions. So I see it as something like that. By presenting these algorithms for students in a step-by-step way automatically, we're allowing them to learn better, learn faster these algorithms and get a better sense of what's possible. Oops. So just an overview of the talk. Or an overview of step-by-step. So we had the big rollout, I think, in 2013 of most of our initial step-by-step programs. Now we have about 100 step-by-step programs spanning math, physics, and chemistry. I think those are the only areas covered. Some of these programs are quite broad, like step-by-step integrate. Some of them are more specific, as you'll see. So to make these programs, we've developed a sort of informal process. And what I like to think of it as is applying the two worlds that I talked about in the previous slide, sort of applying one to the other. So as Stephen likes to say, for any academic field X, there will be a computational X. So I guess this will be computational pedagogy. But actually, we can apply it in both ways. So it's also pedagogical computation. So the obvious way is that we're making these explanations and proofs computable by just programming the logic of these existing methods that exist in the standard curriculum. But actually, the pedagogy informs the internal logic of the programs that we write, and sometimes necessitates the creation of novel algorithms, as we'll see. We can bootstrap off Mathematica to generate some of these step-by-step programs, but we'll need some tricks to prevent Mathematica from evaluating things too quickly, which is what it was designed to do. So I'll show you what that means in the end, but first we'll go through some examples. So before some examples of actual step-by-step programs, just briefly mention some ways in which the best computational theoretical practice diverges from the best educational practice. So I'm not a physicist, but I think Feynman diagrams are something that falls into this category, right? If you're writing a program that computes particle interactions, it's not going to actually draw stuff and like look at drawings internally. Matrix multiplication, as you may know, there's algorithms that are actually more complicated than the standard way, and yet are faster, at least for large matrices. And that's a case where we don't want to teach the students of linear algebra, right, the fastest way to the best way to do it. Geometry proving is an even more interesting case, because if you want to prove something about a geometrical diagram, the best way to do it is to express everything in terms of equations, that is, use analytic geometry, and throw all these equations into something like reduce, or use some Grosvenor bases, and pick out the facts that you want from there. But even in the realm of synthetic geometry, that is axiomatic geometry, there's a divergence between the theoretical and the actual synthetic geometry that you're taught in usually 9th grade in the US. I don't know what other countries do. But so this is an example of a computer-generated proof for 9th grade geometry. But in the theoretical synthetic geometry, we actually reduce the number of notions, and they tend to be somewhat more, not as natural as you'd think. So we have things like signed area, and which is not that complicated, but some other more complicated things to basically speed up and streamline the proving process. So let's get to some, we'll get to some examples. But first I want to define what our goals are for these step-by-step programs. So the first thing to note is that the level of the question should indicate the level of the response that the user expects. It should be grade level appropriate. So think of grade level as sort of a proxy for the kind of response that we're going to give. So this means that queries that are lower level require more intuitive or pictorial or with less jargon explanation. So an example there would be if you put in 5 plus 9, this probably needs to be bigger. So if you plug in 5 plus 9 to Wolfram alpha, you get a step-by-step result. So if this were part of a larger step-by-step program, if you had to do 5 plus 9, it wouldn't give you any steps for this. It would just say 5 plus 9 is 14, right? Because you're obviously doing calculus or something like that. You know this. But if you type in 5 plus 9, you must be an elementary schooler. So you need some explanation for this. So we actually have 2 step-by-step programs for this. One uses a number line where you say start at 0, and then you add 5. And then where you are, you add another 9. And then you say, where am I? Well, now I'm at the number 14. And then there's another one is using what are called manipulatives, which are actually physical little blocks that you play with. Is my internet working? Well, luckily I preloaded most of these.
You may want to disable your wireless.
I was just told that the wireless is probably unplugged with room half in this room.
Oh. Okay. Well, anyway, it just, I'll try reloading it, but, whoa, okay. Yeah, but I plugged in this thing. That's okay, we can do without it, but I'll turn it back on if I can't get it one more time. Oh. Is this just a cache page? I don't know what's going on. I don't know, okay. That's okay. So the manipulatives are just blocks, and it says like you draw 5 blocks, then you draw 9 blocks next to it, and then you just count the blocks, right? Okay, there's actually, it's something like this down here, so I won't bother going to that step by step. They should be complete explanations. And I should say, with regard to number one, as I said, we skipped the showing what 5 plus 9 is at higher level things. But in the future, we're hoping to add a sort of give me some steps for this step. Give me the sub steps, or what do we call it? Show details button. So complete explanations, and of course, given 1 and 2, they should be simple, direct, and standard as possible. So here's some examples. So first is some of the more complex math step-by-step functions. And basically the way they work is you have a list of transformations of how you could transform the given input. And they're applied according to some custom heuristic. So I don't have the internet, so let me just go here. So this is after I press the show steps for do this integral. So here's an example where the standard technique says you should do integration by parts. And if you recall, there's a standard heuristic for choosing which parts should be the integral part and the derivative part. So we use that heuristic. And you do it once to this, and you get e to the 3x sine x times a third, or rather, plus this other term. And again, you're in the case where you usually do integration by parts, so you do integration by parts again. And then the program has to realize that it's going to be in an infinite loop, basically. So, but it needs to realize that, oh, these two integrals are the same, so I can add them together. So it has to have algebra available to apply to solve this problem. Here's a complicated limit. So we're taking the limit of 1 over x, x minus 1 over sine x, 1 plus 1 over x to the x. So the transformation rule we're going to apply is to first do sum of the limits is the limit of sums, or rather the reverse of that. And to take care of that e term there, we apply an exponential and a logarithm, and then we can move the limit inside. So we're trying to write a program that will output the most common steps that a student should be expected to do. But there's some compromises you have to make, and sometimes they come in the form of trying to compromise between having a broad program that can do lots of different problems. If you do that, say you can, or a simpler program that has less transformation rules, right, could still be just as broad, but it might give you like many, many, many steps. And the student might say, why are you doing all this in so many steps when you can just use this trick or something that we didn't include? So there's definitely compromises you want to make here. So we evaluate continuous functions. Just when you see an indeterminate form, apply L'Hopital's rule. What else? Okay. So we have some simple physics formulas. Actually, oops, I didn't mean to press it that time, but it worked. Okay. Okay, so the way that simple physics formulas work is, of course, you just, uh-oh. Okay, let me sign in. Oh, yeah, okay.
Are the explanations generated automatically, or are they written by hand?
They're in between. So there will be somewhere this piece of text will appear, right? And in the code, it'll be joined to these variables. So it's different in different programs. So we'll see some programs that are very sort of simple to understand. I started out with the more complex ones, but some some involve sort of transformation rules that can do all kinds of interesting, unexpected things. Some are more straightforward procedural. So this just basically separates the algebraic part and uses a function called step-by-step simplify to solve the numeric part. But I guess first it just does the dimensional, it converts things into the standard SI units. So that's a fairly straightforward one. So an example of a chemistry one, if you say tryptamine structure, right, you get this, you get a Wolfram alpha output with some pods, and you press step by step, and you get a step by step that explains how to determine draw the Lewis structure. That's the electrons and their bonds between I'm not a chemist. So this is a more straightforward procedural step-by-step program. In fact, it always generates these 5 steps. So first it counts the number of valence electrons, and then it counts the number of valence electrons needed to fill all the shells, the outer shells, and then it applies the bonds in a way that makes sense chemically. I think that's how it works. And then finally, here's an example of a proof. So if you say prove by induction that 3 to the k is greater than k to the 6th, well, of course, that's not always true for low k. So that's what this result is. It's actually proving it's not true. But this is the more interesting case to prove that it is true for k greater than 14. And please show up. So really, a proof is not that different from a step-by-step explanation, except you just know the destination, and it has, I guess, more emphasis on justification. Darn it. Okay, well, that was my last example, so I'm just going to go on since we're close to running out of time. So I want to give you an example of how this works for simple problems where the Mathematica evaluator actually does the right thing. Okay, so an example of that is this really simple example I have. 3 times 2 to the 2 squared minus 3. So that'll be evaluated by the evaluator by Mathematica in the right sequence of steps, which is, as you know, it's called PEMDAS, right? You do the parentheses, then the exponents, then the order of operations, I guess is the other word for it. So we can hold this query, but then if we release hold it, oops, right? It does it all at once. So there's no way to sort of stop in the middle. The key to understanding how to manipulate things when they're being held, I think the one sort of key that helps you do things like this is this technique. So if you map something over a hold, it still gets held. So you could see F could itself be hold of something, and then you could release hold the outer thing, and the inner things are still held. So we're going to do something like that. But we actually have a better version of hold for this purpose called inactive now. I think, I never officially heard this, but do you know if inactive was somewhat inspired by this thing that we're doing to do step-by-step programs?
It came around in various forms, but actually one of the main motivations was partial differential equations. So you wanted to be able to express gradients and curls and things without them evaluating immediately partial derivatives. So you
Oh, okay. Okay. I should have had a step-by-step ODE example as well. Okay, so the way inactive works is basically if you put inactive around a head, and it won't do that head, but everything else, obviously here, will evaluate, and it formats nicely. It formats without showing the inactive. Okay. So what I want to do is I want to put the expression in this form. I want to wrap inactive around each of the heads. And I do this with this little bit of recursive voodoo here, which is, I'm sure there's a much better way to do this, but this is just the way I came up with. So now that I have it in the form that I want, where I've inactivated each of the heads, I can just use the activate function, which activates the specific head that I want. So I'm ready to begin my step-by-step program now. I can just start out by saying there are no parentheses, so let's just do the exponents. That's the E in PEMDAS. So I activate power, and the 2 squared became 4. And I have to evaluate it again to get rid of the inactives. I guess that's because you want to see what happened to the inactives when you do it once. And so in the next step, I could just take whatever I had here, right? Because I said the inactive query is the activated inactive query, so it's still this. And now I activate the times, because next we do multiplication in order of operations. So that's how the times 3, 4 became a 12, and et cetera. The next thing would be plus.
Does it activate the outermost times, like the
All the times.
to the 3 to the 3?
It activates all the inactive times heads. So throughout, it's like a replace all kind of.
Is there a level specification
For activate? That's an interesting question.
In step-by-step,
And step by step there is, but I don't think so. Nope.
no, we decided not to. It's something we experimented with. So you can give a pattern of the specific heads you want to activate. But you can't specify the level. It didn't seem like there was a good use case for activating. You can always use math add if you want to activate a specific part.
So just to push this a little further, I thought to throw in some other, advertise some other neat functions that we have. So I'm going to use this technique to generate a sort of problem generator microsite. So if you haven't heard the Wolfram problem generator, which Brad Janes talked about, it's a site where you can get unique problems and test your metal and find the solutions. And of course, it uses the step-by-step functions once you've tried to answer the question and failed. It gives you a step-by-step explanation. So that's one of the uses we have for our step-by-step functions. So to make a problem generator, really basic one, all you would need is, so all you need for your query is really your held expression, if it's just an arithmetic query. And then everything is done. So ask function, I'm not going to talk all about ask function because I don't have enough time, but really everything is done in this one little line. So this just displays the question, Q, and it tests if the answer, the input, that's what this ask does, is equal to the release hold of Q. And if it is, it says correct. This is the if now is evaluating. And if it's not, it gives you a very Trumpian wrong. So we can actually put that whole inactivate, we can package the previous slide up into a little microsite. I'd have to add cloud deploy here, but I'm not going to because of the web problem. But you could easily just deploy this. So what this one does is say, enter some math. I have to say that this is expecting a held math expression. And then what it does is displays your answer. This is now the answer. Whenever you refer back to ask, if you've answered that question, it just replaces it with the value. That's the magic of ask inside ask function. So replace, I should have said, I don't know why, it should say enter math here. I'm not sure why it's not doing that. But anyway, let's see if it works. So I put in a problem like I was having before. Let's say 4 times 3 plus 3. So this is using the interpreter to make this into a held math expression. And then it's just going to give me a column where I show it, and then I activate the power, and then I activate the times, and then I give you the answer. Hopefully. Submit. Why is it seems to be pinking a little bit. I don't know. What?
It did enter that.
It looks like
Oh, I could. So,
one after the other.
oh, yeah, that sometimes happens. Let's see. Oh, okay. I know what's going on. I just need to do it again. I pressed it too many times without waiting, and it's gonna ask me that many number of times, I think. Yes. Okay. So that's just packaged up that that function. So thank you. And yeah, I was going to give a link to to where you can find all the step-by-step functions for Wolfram Alpha, but I forgot to add that link, but I will add it if you want to download the notebook. So thanks. And welcome to ask any questions.